Hello and good afternoon, everyone. We are group number 2, and we will be the second group in this class to have our video report. And my name is John Paul Nopia, and I will be the first one to report to you about the introduction to electronic communications. So, first off, about communication. What is communication? Communication is defined as the basic process of exchanging information. Communication begins with language, the distinctive ability which has made it possible for the evolution of human society. With language, any message, no matter how complex, can be conveyed between people. Most humans communicate through the spoken word, but a considerable amount of communication is nonverbal. Consequently, the two major barriers in human communication are language and the distance. But with today's technology, it doesn't matter no matter how far the distance you are. You can have communication through Facebook, Messenger, text messages, and also instant emails and such. So now, let's talk about a timeline of milestones in the human and electronic communications. First off, in the year 1830, we have Professor Joseph Henry. He was the person who transmitted the first practical electrical signal. Next, in 1837, we have Samuel Morse invented the telegraph. Telegraph is supposed to be something that he is holding at the moment. Next, in 1876, supposedly, Alexander Graham Bell and Thomas A. Watson invented the telephone. However, with a few research here and there, I found out that Alexander Graham Bell wasn't actually the first one who invented the telephone. He was the first person who patented it successfully, but the first one who actually invented it was the guy whose name was Antonio Meucci. Next comes in 1887 Heinrich Hertz, who discovered radio waves. And next is Guglielmo Marconi. He was the first one to demonstrate wireless radio wave propagation. And in 1901, he accomplished the first transatlantic transmission of radio signals. Next is John Fleming, who in 1903 invented the two-electrode vacuum tube rectifier. In 1906, Lee De Forest invented the tried vacuum tube. In 1923, Vladimir Zworykin invented and demonstrated television. And in 1948, these three people invented the transistor. The first one on the left is William Shockley, the middle will be Walter Brattain, and last but not least, John Bardeen. In 1959, the first integrated circuit was invented. In 1965, the first commercial communication satellite was launched. And last but not least, in 1993, the cellular telephone network was first introduced in the United States. And it should probably took some time before it went here in the Philippines. Because Philippines. Next, I will talk to you about how the electronic communication system works. So, what is electronic communication system? Electronic communications refers to the transmission, reception, and processing of information using electronic circuits. The basic elements of the communication system include the transmitter, the communication channel, or the medium, and last but not least, the receiver. First, let's talk about the sources of information. Sources of information may come from an analog source or from a digital source, so that the intelligence signals may be either an analog or a digital. Analog signals are something continuously changing with respect to time and with an infinite amplitude values. On the other hand, we have the digital signal. Digital signals are something discrete and whose amplitude is of finite value. Next, we have the transmitter. The transmitter is a collection of electronic devices or circuits designed to convert the information into a signal suitable for transmission over a given communication medium. The components of a transmitter are the amplifier, the modulator, oscillator, last but not least is its antenna. Now, let's talk about the different parts of the transmitter. First, as discussed, was the AF amplifier. The AF amplifier, or the audio frequency amplifiers, are used to amplify signals in the range of human hearing, which approximately ranges from 20 Hz to 20 kHz, although some hi-fi audio amplifiers nowadays extend this range up to around 100 kHz, while other audio amplifiers may restrict the high frequency limit to 15 kHz only or less. Next comes the modulator. Modulator is a radio frequency modulator or RF modulator which takes a baseband input signal and then output a radio frequency modulated signal. This is often a preliminary step in a signal transmission, either by an antenna or to another devices such as the television. Next is the RF amplifier. It is a radio frequency amplifier or the RF amplifier who is tuned amplifier that amplifies high frequency signals used in radio communications. The frequency at which maximum gain occurs in an RF amplifier is made variable by changing the inductance or the capacitance of the tuned circuit. So most capacitor use is the variable capacitor to change the amplification. And last but not least, which will not be listed here, is the antenna. Antenna is used to receive or to transmit the signal waves. Now, the next part of the electronic communication system is the communication channel or the medium. The communication channel provides the means of transporting signals between a transmitter and a receiver. The two general types of communication media are the guided or the wired and the unguided, which is the wireless, which is mostly used in radio waves. Examples of guided media are the coaxial cable, the fiber optic cable, and the waveguide. And this just shows how a wireless signal works, like Wi-Fi for example. Although the medium supports the transmission of information, it also attenuates it and causes the received signal to appear much lower in amplitude. However, considerable amplification of the signal is required for a successful communication. And last but not the least of the electronic communication system are the receivers. Receivers are a collection of electronic devices or circuits that accept the transmitted message from the channel and convert them into a form understandable to the human being. The components of a receiver are the amplifiers, the modulator, and also the antenna, which is described as earlier. So this will be an antenna, the RF amplifier, then the modulator, and the audio amplifier. And you can connect here either a speaker or anything that you can use to hear something, such as earphone jack or whatever. So what is a demodulator? from the receiver. The demodulator is a circuit that is used in amplitude modulation and frequency modulation receivers in order to separate the information that was modulated into the carrier from the carrier itself. The demodulator is the analog part of the modulator. A modulator puts the information into a carrier wave at the transmitter end, and then a modulator pulls it so it can be processed and used to the receiver's end. And lastly, let's talk about the limitations of the communication system. There are two limitations in electronic communication systems, which consist of the noise and also the bandwidth. First off is the noise. Noise is any unwanted form of energy that tends to interfere with the proper and easy reception and reproduction of the desired signals. This is one of the major problems in the communication systems. For example, it has been countered back in electronics too, which can be seen on the prototypes and such. Next is the bandwidth. Bandwidth is the portion of the electromagnetic spectrum occupied by the signal. It is also the frequency range over which an information signal is transmitted or over which a receiver or other electronic circuit operates. Also, it can be described as the difference between the upper and the lower frequency limit, which can be seen in this formula. Bandwidth is equal to F2, the upper, minus F1, which is the lower limit. Next is the information capacity. Information capacity is a measure of how much source information can be carried through the system in a given period of time. And last but not the least, Hartley's law. It states that information capacity is directly proportional to the bandwidth and the transmission time, which can be seen in this formula. I, which equals to information capacity, is directly proportional to the bandwidth multiplied by the transmission time. And that will be all for my report. Thanks for listening.
Good afternoon, everyone. My name is Bebeth Olivar, and I will report about the mode of transmission. What is transmission mode? The term transmission mode defines the direction of flow of information between two communication devices. In electronics communication, there are two types of transmission mode. The first one is the one-way communication called the simplex or broadcasting, while the other one is the two-way communication called the duplex. The duplex consists of half duplex and full duplex. First, we will tackle about the simplex mode. In simplex mode, the communication is unidirectional, as on a one-way street. Only one of the two devices on a link can transmit, while the other can only receive. The simplex mode can use the entire capacity of the channel to send data in one direction. There is no mechanism for information to be transmitted back to the sender since communication is unidirectional. A television broadcast is an example of a simplex transmission. Another example of simplex transmission is a loudspeaker system. An announcer speaks into a microphone and his or her voice is sent through an amplifier and then to all the speakers. Fire alarm and wireless remote control work the same way also. Next is the half duplex mode. A half duplex system can transmit data in both directions, but only in one direction at a time. That means half-duplex modes support two-way traffic but only in one direction at a time. The interactive transmission of data within a time-sharing system may be best suited to half-duplex lines. Both the connected devices can transmit and receive, but not simultaneously. When one device is sending, the other can only receive and vice versa. As shown in the figure, computer A sends information to computer B. At the end of the transmission, computer B sends information to computer A. Computer A cannot send any information to computer B while computer B is transmitting data. This is generally used for relatively low speed transmission, usually involving two-wire analog circuits. Due to switching of communication direction, the data transmission in this mode requires more time and processes than under full duplex mode. A walkie-talkie is an example of a half-duplex mode. A walkie-talkie operates in half-duplex mode. It can only send or receive a transmission at any given time. It cannot do both at the same time, as well as the sonar and amateur radio. Next is the full duplex mode. A full duplex system can transmit data in both directions on transmission path. Full duplex method is used to transmit the data over a serial communication link. Two wires needed to send data over a serial communication link layer. Full duplex transmission, the channel capacity is shared by both communicating devices at all times. Both the connected devices can transmit and receive at the same time, therefore it represents a truly bidirectional system. The link may contain two separate transmission paths, one for sending and another one for receiving. Full duplex mode is used when communication in both directions is required all the time. The capacity of the channel, however, must be divided between the two directions. An example for this is a telephone network in which there is a communication between two persons by a telephone line through which both can talk and listen at the same time.
Hi, this is Paul Jerome G. Medina and I will be reporting electromagnetic spectrum. What is an electromagnetic spectrum? The electromagnetic frequency spectrum refers to the entire range of usable frequencies. It extends from a few hertz to cosmic rays. As you can see from the diagram, it refers to the entire range of usable frequencies. The lowest frequency range is 10 raised to 0, which is subsonic, and the highest frequency range is 10 raised to 20, which is the gamma rays. What is a frequency? It is the number of times an alternating current goes through its complete cycle per second. The international unit of measurement of frequency is Hertz, abbreviated as Hz. Now we go to the International Telecommunications Union (ITU) band designations. As you can see in the picture, there's the band number, frequency range, and designations. Band number 2, ranging from 30 Hz to 300 Hz, is the ELF, or extremely low frequencies. Band number 3, ranging from 0.3 kHz to 3 kHz, is the VF, or voice frequencies. Band number 4, ranging from 3 kHz to 30 kHz, is the VLF, or very low frequencies. Band number 5, ranging from 30 kHz to 300 kHz, is the LF, or low frequencies. Band number 6, ranging from 0.3 MHz to 3 MHz, is the MF, or medium frequencies. Band number 7, ranging from 3 MHz to 30 MHz, is the HF, or high frequencies. Band number 8, ranging from 30 MHz to 300 MHz, is the VHF, or very high frequencies. Band number 9, ranging from 300 MHz to 3 GHz, is the UHF, or ultra high frequencies. Band number 10, ranging from 3 GHz to 30 GHz, is the SHF, or super high frequencies. Band number 11, ranging from 30 GHz to 300 GHz, is the EHF or extremely high frequencies. Band number 12, ranging from 0.3 THz to 3 THz, is the infrared light. Band number 13, ranging from 3 THz to 30 THz, is the infrared light. Band number 14, ranging from 30 THz to 300 THz, is the infrared light. Band number 15, ranging from 0.3 petahertz to 3 petahertz, is the visible light. Band number 16, ranging from 3 petahertz to 30 petahertz, is the ultraviolet light. Band number 17, ranging from 30 petahertz to 300 petahertz, is the X-rays. Band number 18, ranging from 0.3 exahertz to 3 exahertz, are the gamma rays. And lastly, band number 19, ranging from 3 exahertz to 30 exahertz, are the cosmic rays. Extremely low frequency or ELF, ranging from 30 to 300 Hz, includes AC power line frequencies as well as the low end of human hearing range. Also, ELF should not be confused with other low frequencies, namely low frequency LF and very low frequency VLF. Difficulties of ELF communication. One of the difficulties posed when broadcasting in the ELF frequency range is the antenna size. This is because the antenna must be at least a substantial fraction of the size in at least one dimension of the wavelength of the frequency of the EM waves. Simply put, a 1 Hz cycle per second signal would have a wavelength equal to the distance EM waves travel through your chosen medium in 1 second. For ELF, this is very slightly slower than the speed of light in a vacuum. Other uses of ELF communication. Transmitters in the 20 Hz range are also found in pipeline inspection gauges, also known as PIGs. Some radio hams record ELF or even lower signals from very large homemade antennas and play them back at higher speeds to catch natural fluctuations in the Earth's electromagnetic field. Increasing the playback also increases the pitch, so that it is brought into the audio frequency range. Naturally occurring ELF waves are present on Earth, resonating in the region between ionosphere and surface. They are initiated by lightning strikes that make electrons in the atmosphere oscillate. True VLF signals were predominantly generated from lightning discharges. It was found that an observable ELF component, slow tail followed by the VLF component, in almost all cases. Ultra-high frequencies range from 300 to 3000 MHz, a widely used portion of the frequency spectrum including television channels 14 to 83, land mobile communications, and cellular telephones. The uses of UHF band. The UHF band is extensively used for satellite communication and broadcasting, in cellular telephone and paging systems, and by third generation 3G wireless services, because the frequency is high and the band is vast, a span of 2.7 GHz from the low end to the high end. Wide band modulation and spread spectrum modes are practical. Channels and subbands within the UHF portion of the radio spectrum are allocated by the International Telecommunication Union or ITU. Super high frequencies range from 3 to 30 GHz. These are microwave frequencies that are widely used for satellite and radar communications, also known as the centimeter band or centimeter wave, as the wavelengths range from 1 to 10 cm. The uses of super high frequency. Given their ability to carry enormous amounts of data, super high frequency waves are used for relaying broadcast programs such as STL, TSL, and TTL. For radar, example, weather, and etc., satellite communications and satellite broadcasting, and other applications. Denki Kogyo provides a parabolic antennas of each diameter and FPU rotating equipment, as well as reflector panels and other equipment essential for microwave communication circuit. Extremely high frequencies range from 30 to 300 GHz. Only a limited amount of activity occurs in this range, including satellite communications and some specialized radars, also known as millimeter wave. One of the greatest and most important uses of millimeter waves is in transmitting large amounts of data. Every kind of wireless communication, such as the radio, cell phone, or satellite, uses a specific range of wavelengths or frequencies. Each application provider, such as a local television or radio broadcaster, has a unique channel assignment. so that they can all communicate at the same time without interfering with each other. These channels are bandwidths, also measured in either wavelength or frequency, that must be large enough to pass information from the broadcaster's transmitter to the user. For example, a telephone conversation requires only about 6 kHz of bandwidth, while a TV broadcast, which carries much larger amounts of information, requires about 6 MHz. A kilohertz is 1,000 cycles per second. A megahertz is 1 million cycles per second. Increases in the amount of information transmitted require the use of higher frequencies. This is where millimeter waves come in. Their higher frequency makes them a very efficient way of sending large amounts of data, such as computer data, or many simultaneous television or voice channels.
Infrared refers to radiation generally associated with heat. It is used in astronomy to detect stars, remote control units, guidance of weapon system, or optical devices. Infrared waves are longer than those of visible light, just beyond the red end of the visible spectrum. It falls in the range of the spectrum between microwaves and visible light. It has frequencies from about 0.3 to 300 terahertz and wavelength of about 30 centimeters or 12 inches to 714 nanometers, although these values are not definitive. These are some uses of infrared. Facts about infrared. Almost half of the energy arriving to the Earth from the Sun comes as infrared light. Anything which has a temperature puts out heat or infrared light. Infrared waves are also given off by stars, galaxies, lamps, flame, and anything else that is warm, including you. Infrared light can travel through thick smoke, dust, or fog, and even some materials. In firefighting, infrared cameras are being used to locate people or animals in heavy spots and to detect hotspots in forest fires. Humans at normal body temperature radiate most strongly in the infrared at a wavelength of about 10 microns. Humans may not be able to see infrared light, but snakes in pit viper family have sensory pits which are used to image infrared light. Infrared ovens were the first oven. However, the hot air dried the food up and these ovens thus replaced by microwave ovens. Visible spectrum is the portion of the electromagnetic spectrum that is visible to the human eye. A typical human eye will respond to wavelengths from about 390 to 700 nanometers. It has frequencies from about 0.3 to 3 petahertz. This is the range of visible light as shown in the picture. Facts about visible spectrum. Our eyes can recognize each wavelength by a different color. Red has the longest wavelength and violet has the shortest wavelength. Cones in human eyes work as a receiver for these small visible waves. Some other creatures can see parts of the spectrum that are not visible to us. For example, some insects can see UV light. Wavelength. Wavelength is the length that one cycle of an electromagnetic wave occupies in space. The length of the wavelength depends on the frequency of the wave and the velocity of the light. Wavelength is equal to velocity factor, which is equal to 1 in free space times the speed of light in free space divided by the frequency. At high frequency, the wavelength is too short and is usually expressed as angstrom. Example: light with a frequency of 7.26 times 10 raised to 14 Hz lies in the violet region of visible spectrum. What is the wavelength of this frequency of light? Since wavelength is equal to velocity factor times the speed of light, which is 3 times 10 raised to 8 meter per second, divided by the frequency of light, which is 7.26 times 10 raised to 14 Hz, we can get the wavelength, which is equal to 4.13 times 10 raised to negative 7 meter or 413 nanometer.